Next thing we need is a way to predict U, the flow rate of the water as it exits the rocket. So this equation we're looking at is called Bernoullis equation, and it's a statement of energy conservation for a fluid. So we have three kinds of energy here. It probably looks like kinetic energy, 1/2 mv squared, but rho here represents the density, which we know is just the mass per volume. So this is the kinetic energy per volume. And we're going to call it bulk kinetic energy. What do I mean by bulk? If I have some bulk of fluid flowing at this speed, that's going to be the energy associated with that bulk of fluid. Here, I know mgh would be the gravitational potential energy, and we're working in a per volume way here. This is really common when we deal with fluids, is to deal per unit volume. This is the gravitational potential energy. Pretty simple. And then finally we have pressure, and pressure is another kind of kinetic energy, but it's the thermal Ke, kinetic energy. Or you could say that it's the molecular kinetic energy. So this is energy per unit volume associated with the jiggling of the molecules in the water or in the gas. So we have the bulk Ke, the thermal kinetic energy, and gravitational potential energy. And as the fluid flows, we can transfer between these forms, but if we have a fixed amount of fluid, we're going to have a fixed total amount of energy, aside from work being done. What can we do with this? Well, let's see. I can first multiply by 2 to clear this 1/2, and divide by rho. So I'm going to get u squared by itself, and then I have 2gh, I got rid of my rho here, and we had to tuck the rho somewhere, it ends up under this p. So we divided every term by rho, saves us 2 rows at the expense of having just 1, so that's nice, a little bit simpler, and we just move the 2 over to this product. So this is still Bernoullis equation, it's the conservation of energy. Taking that equation, I know that the change in potential energy, at least during the time that we're ejecting this fluid, gravitational potential energy, that's not really going to be a significant effect. So we're just going to associate the speed here, the bulk kinetic flow, with liberation of energy from the pressure energy here. And we can account for this energy in our Newton's second law equation by talking about the work done by gravity. So we've got the bulk kinetic energy and the pressure kinetic energy, and the sum of the two is going to be a constant. What that means is I can take the expression that looks like this, throw some initials on here, U initial, P initial, or U final, P final. When I take the total, I'm going to get the same quantity either way. So setting those equal to each other, I know U initial squared, this is the flow of water out of the rocket, plus 2pi over rho. It's going to be U final squared plus 2pf over rho. So one thing we commonly do when we're looking at an expression like this is put all the u's on one side and put all the p's on the other side, and that'll give us an expression for the change in velocity associated with some change in pressure. So let's see how that works out. Here we've put our difference in velocity squared on one side and our difference in pressure on the other side, and there's actually a name for this difference between the pressure in the rocket and the pressure that we're ultimately talking about, which is the atmospheric pressure. So if we measure pressure with a gauge, like we have on our bike pump, what you're really measuring is the difference from atmospheric pressure. So your bike pump says 0 when it's not doing anything, but the pressure inside the bike pump isn't actually 0. The pressure is 101.3 kilopascals. So that's atmospheric pressure. However, we don't measure that. We just measure the overage, how far above atmospheric pressure we've pumped our gas. And that's usually the meaningful thing when we're actually working with pressure in a real system. So we call this the gauge pressure because it's the pressure that would be measured by a gauge. And we can just call that P sub G, PG. So what we can do, taking the square root of both sides and noting that the rocket starts at speed 0, so the flow rate of water out of it is also 0, the final speed is just going to be, take the square root of both sides, and we see it's the square root of 2 over the density times the gauge pressure. So that's pretty simple. we now have our expression for the flow of water out of the rocket as a function of the pressure, and a way to get the pressure as a function of the change in volume, and those are the two goals we had.